So yeah, this talk is about a tool you can use for load regulation in Erlang programs called Safetyvalve. Safetyvalve owes all of its existence to Ulf, which is sitting right down here, because he wrote an application called Jobs a couple of years ago, and which I didn't want to use. So hence I tried to write my own. No, I really had to investigate different paths. This is why, essentially, I wrote Safetyvalve. But Ulf will be talking about Jobs right next after this talk, so you'll get to enjoy that as well. This talk is a little bit about what load regulation is in general, then how you use the Safetyvalve thing, and then how this Safetyvalve thing is tested. Because the main focus of Safetyvalve is to have proper tests of the load regulation framework. And the reason being that this becomes a very central part of your application, so it better has to work correctly, otherwise your system is host. So the basic idea of load regulation is to protect your Erlang system against the overload situation. So you have a system, it's built to handle, say, 40,000 simultaneous connections, and all of a sudden, due to you being popular on Hacker News or something, you have 60,000 connections you have to handle all of a sudden. Now, how does your system act or react in that situation? Does it handle the 40,000 and then deny the extra load of 20,000 connections? Or does it just degrade into a point where no connection at all goes through because it tries to take more load than what it can handle? Or does it just crash and do something really horrible? So the idea of overload protection is to basically build a system inside your big application that allows you to limit load on the system so you can keep at a certain level of load, and you can certify your system to work at a certain level, right? So that's step one, and I tend to call that load regulation. The second part is load normalization, that when you get in requests, they might arrive as spikes. It might not be a uniform distribution where new requests arrive at uniform rate. No, they might arrive all of a sudden a lot of things in a short time frame, and hence you want to queue your excess spike and then distribute it over a little bit of time so you normalize the load on the system. And this can have impact because you might have a process set up inside there that takes a little bit of more resources when it's set up, but once it's running, it might go back and have a steady resource consumption. So the spike then works like an amplifier, so you might run out of a certain resource quickly unless you have some kind of normalization going on. So that's the basic idea of doing overload protection on the system. Safetyvalve is, as I said, a load regulation framework like Jobs. There's a built-in overload protector in the OTP system called Overload. I'm not sure how many uses it, but it's there, and it's kind of like the same idea. The basic idea is that you ask these systems whenever you get a request into the system, you ask these systems, is this request allowed or denied? And based on whether or not the overload protector says that I'm in an overload situation, or it says I'm fine, you get to run or deny the request. That's the basic idea and the basic gist of it. They're different in the way they work, and they are built for, I think, different purposes. So I think both Safetyvalve, Jobs, and Overload have their uses. It's not that one is better than the other, and they are really built for different things. Safetyvalve works by tracking essentially three main things. It tracks a concurrency count, which basically means that it tracks for a given type of task inside your system how many workers are there of that task type. So basically that's the first thing it tracks. What is my current concurrency count for this given task? Then it tracks a queue for if it hits the concurrency limit, then it can begin queuing extra work up to a point. There's a queue size, and if the queue size grows full, it'll begin denying work by a tail drop by default. So that's the second kind of metric you have inside the system next to the concurrency count. And then there's a frequency rate at which it allows work to dequeue from the queue. So the rate defines how fast it'll be able to do things, and this has to do with the normalization part, that we normalize the load. So we do not, if all of a sudden all of concurrent workers, they are just finished like a snap, then we do not want all of the queued workers to come into the system at the very instant. We want them to come in at a steady rate. The way it works internally is that it is what is called a token bucket regulator. So it has a gen server process that basically sits and adds tokens onto a bucket. And in order to get dequeued, you need to pair yourself with a token. And tokens pours into the system at a steady rate. Now, the idea is this is the rate limiting, but it does allow for small surpluses of extra tokens if there's nothing in the queue ready. So in the case that we have no work, we allow for a small surplus of tokens, and that's very typical of token bucket regulators. The idea being that if the system has been idle for a little while, then we might be able to take a small spike burst at the very beginning of initial work. So this is why you allow a small surplus of extra tokens in your token bucket regulator when the system starts up. The thing is that the overload thing built into OTP has no queuing facility. It's basically you ask it, it says yes or no. Based on that, you get whether or not you are to run or not run. So essentially, overload works with a queue size of 0. For some workloads, that is exactly what you want. You do not want to queue, because if your expectation is that there will not be a freed resource in a short amount of time, there's no reason to try to queue a resource if you expect there to be 5 minutes before the resource becomes available. Then it's better just to deny him right away. But say you have a lot of small web requests going into the system, and they are very, very short in this time span they have, then it might make sense to queue them for a little bit in order to basically take them a little bit later, because the churn rate on the system is pretty high in that case. So whether or not, how much queue you need and whether or not you need any queue can be based upon the fact of what is your current churn rate in the system. And that essentially is a difference between, say, overload and Safetyvalve. Safetyvalve allows for this queuing, overload doesn't, but for certain workloads, it's completely okay not to have this kind of queuing. What I did in Safetyvalve a couple of months ago was that I began looking at CoDel or control delay. So how many here has heard about the word buffer bloat in TCP? There's a couple, that's good. So if you do not know what buffer bloat is, you should go and look it up. It's important. It's very important. It's a problem that TCP has, and it is actually kind of related to what Steve was just talking about with MyTP, and the reason MyTP got added on top of the BitTorrent protocol, or they exchanged TCP for MyTP in the BitTorrent protocol, or in the BitTorrent system, exactly for this reason. The problem has to do with that in the internet network, we have buffers in front of each router or switch in the system, and especially your ADSL modem at home has a buffer. Network cards has buffers, usually 1,000 packets or something like that. They can take 1,000 packets on that buffer because they are 10 gig interfaces today. And all these buffers means that when you operate TCP, you will begin having what is called standing queues in TCP. These buffers will be half full all the time, or full all the time up to a certain level. And since TCP is only using packet loss as a way to determine whether or not it has troubles, it means that these buffers fill up and you will have a standing queue in the buffer all the time. That's the gist of the problem. Now these standing queues, you have a sojourn time through the queue. You have to go through all the queue before you get dequeued and go on to the next hop on your route. This means you have just incurred latency on your link. Right, so that's one problem, and this is what, for instance, hurts real-time communication over the internet, because all these standing queues just adds to the latency all the way through. What is worse is the small ADSL modems you have at home, because they usually only have a 10-packet buffer. And as soon as you have BitTorrent running, it'll fill up that buffer with all its packets, and now your Skype call cannot go through, and now you're in trouble. LEDBAT is one idea, which Steve talked about in the last session. LEDBAT is one idea for tracking this by tracking the delay on the packets. Van Jacobson and Kathleen Nichols has this CoDel algorithm as a way to solve it. And the most important thing, I think that what led Jacobson, or God as we tend to call him, onto this thing was that he figured out that in most TCP systems, packet arrivals are not Poisson distributed. People would think that arrival rate can be explained by Poisson distribution. Most academics would use that distribution, but it isn't true. Data is arriving and is very dependent. And it kind of makes sense because say you are in an HTTP web server and I'd make the first request towards it for an HTML page. Well, right next after, there'll be a request for the JavaScript, for the CSS, for the JPEG images, and so on. So there's dependency here going on. The first request is essentially spawns other requests that will go through. And that is also true in TCP. I have a window that I can fill up. So when I see that I have an ACK back, I can fill up the whole window. So things will not arrive in a general Poisson distribution. And that is a very important thing when you look at TCP at least. So my idea was to say, well, this control delay queuing is interesting. Let me try to apply to the queue inside Safetyvalve. Because that might actually be useful. The problem here is that if I have a large standing queue in Safetyvalve, I have the same problem, that I'm waiting in the queue until I can get to do work in my system. And that becomes a problem because then I have to tune the queue size, but I do not know the queue size of my system unless I measure it. That is a problem. I want a system that is self-tuning. So CoDel is a self-tuning algorithm, hence I thought, well, let me try to use that. So what is the basic CoDel trick? The basic CoDel trick is that whenever you enter a packet on a queue, you take its timestamp. And whenever you dequeue the packet, you have a timestamp as well. And the difference between those two is called the sojourn time. That's the time we spend in the queue. Now note that compared to other systems like random early detection and other active queue management algorithms, this tracks the time in the queue. It doesn't track the size of the queue. It doesn't track how many bytes are in the queue. It tracks the time we went through the queue. And then very simply, if we have a sojourn time in the queue that has been too high for too long, given by a target we set, we begin dropping packets. We begin front dropping from the queue. We begin dropping work out of the queue. And that should then pull down the queue size again. So we begin selectively, randomly denying work if the queue goes too high. And that means we can define a target. We can say we want to spend at most 25 milliseconds in the queue. That's our target. And then this algorithm will basically begin doing this kind of management on the queue. So if we get a sojourn time that's longer for too long, it'll begin dropping out work until we get down again. So this is the basic idea. The only thing I'm missing currently, and this is why it's experimental, is that the producer must react to work rejection by lowering its initial send rate into the system. So it's only useful if you have a feedback mechanism like in TCP where you can essentially turn down your rate, because that is what happens in TCP when this happens. Essentially, this system is sitting and watching over the queue size, and when the queue size in TCP grows too large, it'll kill a packet, but that packet loss then feedbacks to the TCP protocol. That TCP protocol will then say, well, let me close down the window, because obviously there's loss on the line, so it must be congested. And that is exactly what fixes the problem for TCP. Now, in order to use it completely in Safetyvalve, you will need to have some kind of TCP-like additive component with kind of like a window. You want to spawn, say, if you have control of the work you spawn, you have to feedback up and hope that the guy you feedback to has some way of stopping the bumping on the system, right? So there's a control flow algorithm you have to do. But it can tell you when you have a too long sojourn time and when you should, when it will begin rejecting work on the queue. So I said this. The details is in a ACM article called Controlling Queue Delay by Van Jacobsen and Katie Nichols. It's really worth reading. If you're interested in anything with TCP protocols and stuff, this is the paper essentially to read. They essentially take the survey of all of what they did in a couple of years and then have built the essence of it into this paper. So it's really worth reading. So it's currently a quite experimental feature inside Safetyvalve, and it's not that used right now. But I hope to build the part that does the TCP additive stuff on the front of it, so you can really use this. It ties together with all these ideas of having to or needing to do something about your queues. Tail dropping a queue is wrong. You need to do something else. You need to do active queue management on queues when they become full. And the reason is, of course, that it takes time to walk through the queue. It takes time to sojourn through the queue, and that means that you have a standing latency. By the way, this is what Node.js is missing. So how do you use it? Well, this is the configuration part you would write in your config file in the Erlang system. It defines that I want a queue here with a name, and then I have a prop list that sets some settings. This is more or less modeled like from jobs. Jobs has kind of like the same way of setting queues, so I'm totally in debt to Ulf for that. You set a rate at which you want to replenish the tokens in the token bucket regulator. You set how many tokens you want to replenish with. There's a limit on the burst, so if there's no work, you would at most have 30 tokens ready to take the initial burst. The queue has a size of 50 in this configuration, and you may at most have 32 concurrent workers at a given point. So this is a very limiting construction. The way you use it is, suppose that we have this with PostgreSQL on a query function. And this is probably not crash safe, but please ignore that. So the idea is I obtain some connection, I run my query fun, and then I put back the connection into a pool. And I want to protect this pool. In this case, I want to protect some foreign system against an overload situation. So there's two ways you can use a load regulator. You can use it to protect your system from the outside by telling the outside that I'm overloaded, or you can protect one other system that cannot cope with your load, which is very common in Erlang. So in here, I want to protect the foreign system by imposing some kind of regulation on the foreign system. And then the second part is that how do you run it? Well, you wrap your with PG call in a fun, and then you call Safetyvalve run on it. This is again very jobs-like. What you get back is either that you get OK rest back if you have a result, which is OK in here, or you get some error with a reason. And the reason could be that you are denied to do the job because the system is currently overloaded, or you're denied to do the job and the queue is full. There's no more space in the queue. Or you are denied doing the job because CoDel has told you that it has dropped you off, essentially. So you're not allowed to run for that reason. Internally, it works by you having a gen server and you ask it to do work, and then when you get an OK back, you're blocking on that, and when your process gets an OK back, it can do its work, and then it can tell back that it's done. So it's an as-done pairing that you use internally in order to solve this. Yeah. So this is more or less how the system runs, but that is, you can say, one of the more interesting parts, and the reason why I wrote this is actually this manifesto. This system is more or less has a rule when you want to write programs. When you want to write this system, you're writing them according to this manifesto. And it is inspired by Dorme 95, which is a Danish set of movie makers, and they put down some constraints on themselves in order to produce art. And the things were, for instance, that you are only to use a handheld camera, you may only use natural lighting, and you only have one take per scene, stuff like that. So they imposed a lot of constraints on themselves in the hope that they could produce better art by doing so. So let us do the same for programming, right? So the first thing is, in this manifesto, you're only allowed to write code when you know how to test it. That's pretty standard. But a test is a QuickCheck model. A test is not a unit test. It's a QuickCheck model. Essentially, I want to banish unit tests. I hate them with a passion. So a test is a QuickCheck model of what we are trying to achieve. And then there's a rule that says that there's a dogfooding principle. You may only write a feature when somebody has the need for it. You're not allowed to write it before. And this is because I see so many libraries where people just cram stuff, and oh, we can also do in some way. And the result is just that you get a bloated mess nobody can maintain. So there's a dogfooding principle. And then the final thing is never discuss indentation. This rule actually is stated a bit different in the manifesto. It says that you're only allowed to discuss indentation when all other important decisions has been solved. That includes design, algorithm choice, data structure choice, etc. Right? So essentially never. How do I test it? Well, the basic philosophy that I use is that many people who try to do QuickCheck stuff, they start out by saying, let me build a complete specification of the full system. And that usually fails. And the reason it usually fails is because your full implementation is essentially the thing you're trying to test. So your model ends up being the same as the system under test. And then you're testing nothing. You have two equivalent implementations, nothing is gained. So instead, what you want to do is you want to have many, many, many small, very naive QuickCheck models. And each model only tests a single aspect of your system under test. So you're essentially hitting it from all kinds of directions. And the hope is that one of your small model tests actually hits something important in there. And then you want to have QuickCheck and the random model generation of QuickCheck as an amplifier on your simple test. So you write a simple naive test, and then you use QuickCheck as the amplifier by randomizing this test all over and over again. And that randomizes the amplifier that makes you able to actually do really interesting stuff and find a lot of bugs in your code. So always prefer more tests. That's the generic philosophy, rather than having a simple one, single one that has all the specifications. So the second trick is simplify. When you do this, you want to simplify stuff. Simplifying stuff means that the first trick is that one of the things you could do in QuickCheck is you could say, I do not care about results. I do not care about push conditions. I generate random commands, I fire them off to my system, but the system must not crash. The system should be total, it should return in time, and it should be crash-free. That's your first test. That's your first QuickCheck model, totality. And that's very easy to write. But it will check that all these commands I bump the system with random crap will not crash the system, right? So that's the first trick. You can always write this test almost all the time, even though you try to grab for something higher later. This would force you to have a model and a specification. The second trick I use is I make a degenerate model. So in this system we have concurrency, we have queue size, and we have the size of the token bucket regulator, the rate of the token bucket regulator, and how many, and then also how many surplus tokens we can have in the bucket regulator. So these are three main values. So we limit them. We say the queue size can be 0 or 1. The concurrency count can be 0 or 1. And the bucket size can be 0 or 1. So we limit them down, even though the system in reality can handle arbitrary natural numbers in these positions. We build a test without that, just to keep it simple. And this will probably find errors anyhow. In fact, it did. So that's the second trick. The third trick is that you have a queue inside here. So you might think that your model should track what is inside the queue, what is not inside the queue. But you can simplify. You could say, well, let us just track how many elements are in the queue. We do not care about order. We do not care about when things enter or when things leave. We just care about how many are in there. That's a grave simplification, but chances are it'll find things. And we can write a separate test, the test that our queue is actually preserving order. And that is actually a simple test to write because we have a queue module in OTP, so we can just use that as a base. That is our model, and then our system under test is a faster queue. and then we just run them in tandem and check that they produce the same result. So it's easier to check the queue for ordering. So why add that to this more complex specification, right? We can skip that. So that's another trick. Simplify by only counting stuff. You have a dictionary, what is the size of the dictionary? Chances are it might find a bug. The third trick is that you are allowed to hack your code all that you like. So I often add specific query commands to my systems so I can query their internal state and get it out in some simple pre-specified way. That helps post conditions. I can ask what is the state of the system while it's doing stuff. That helps a lot. So feel free to hack your code in ways that makes it possible to do more efficient testing. That's essentially what you want to do here. Time is usually a problem in most QuickCheck tests. And the reason is the time is something that happens in the system while your test is running and you have no control. That is a problem because you do not have control of time and your model wants control of time. So the trick is to inject time. You let the model generate what time it is and then tell the system what time it is. And there are several ways of doing this. One way is to use a tool like mech and then hack the OS timestamp function and decide what time it is in the running system, but then time won't progress. So that is one thing to look out for. The other thing you can do, which I tend to do, is nowadays I make my systems actually take a timestamp value as an extra parameter. And then the default is that you do not supply the parameter, so it takes OS timestamp or Erlang now, depending on what it needs, and then it injects that into the call, and then things work. But now the test case, the model, can override the time and say, oh, the time is, by the way, this. So now I control time in my model, and that means I can have an advanced time call in my model that tells now time advanced. Now something happened with time. So that allows me the freedom to control time from the model, and that simplifies my system under test. And this, again, goes hand in hand with hack your code, so it's easy to test it, or easy to build a model for it. The way this system is kind of like I have processes that I need to go and they need to hit a gen server and wait for a reply and stuff. So I have a very non-deterministic system, basically. And there are ways to handle that with QuickCheck, but this is the low-level way that would work basically everywhere. What I do is I issue my commands and then I wait for a fixed point. Basically, I look at process info for certain processes and I make sure that they're all sleeping, blocked on receives, and not doing anything. I track all the reduction counters for those processes, and then I check again that the reduction counters did not bump in the meantime. And if they bump, I'm not at the fixed point, so I keep on running until I hit the fixed point. That's the basic idea. So I'm making sure that when I issue a command, I essentially issue a command to the system, and then I twiddle my thumbs until the dust settles. And when the dust settles, I can issue with the next command. So I'm basically waiting around until this happens. I could wait with a timer and say sleep 1 second, but that would make my test cases slow. Yeah? How would you know which processes to run? So the situation here is that I know exactly what processes I have. So I'm only interested in the set of processes that could affect the system. In general, you cannot do this. You need to know what set is eligible for changes, and you need to be sure that nobody outside can prod them, because in that case, you wouldn't be able to do this. So that's an important point, yes. You need to know what set you have for doing this. QuickCheck can do stuff with this as well, so you can actually use QuickCheck to do some of these things. There are other ways around it, but basically you need to know when you hit the fixed point. And then one of the tricks that I also utilize a lot is that in QuickCheck you have these data models, which basically means that I have a series of commands, and the commands are dependent on each other. So the first command defines what the next command can be. The next command defines what the next command can be. That's a data model for because your model is stateful. It tracks state between your commands. But it also enforces you to do complete post-condition checks. You have to check the post-condition at each step of your chain. So one of the tricks you can do is you can actually say, well, what I need is I need a system that is in a valid state. And then I do a single command on it and check that the single command has a valid observation. So how do I generate an initial valid state? Well, I can construct it directly by defining a generator that constructs that thing. I could do that in QuickCheck. So I could say, let me build up a structure which is valid. But that's hard in general. A better trick is actually to say, well, let me start with an initial state and then just prod it randomly with commands, but ignore the output. That means now I have some state which is valid because I generated it only with the commands that I can issue to the system. And now I can do my observation on my generated random thing. But I'm not checking all the states up to that point. I'm only checking the last step. And that's usually way simpler than checking every step on the way. So sometimes that works. The CoDel thing inside is checked by that. So basically it generates a random sequence of insertions and queuings, and then at the final step we try to dequeue, and then we do an observation based on what that dequeue should do. So the main queue is checked by this observation. This observation is that you have 3 bits of information, namely you have the queue size, which can be 0, 1, you have the concurrency count that can be 0, 1, and you have the bucket size that can be 0, 1. So these are the 3 possible values you have in there. That gives, there are 3 commands you can do. You can tell that time has passed, so the bucket gets replenished with new tokens. You can ask for work, that is, we can have a worker that goes in and asks for work, or we can have a working worker, that can only be 1 in this case, that says, I'm done. So there are 3 bits, and there are, that gives 8 different bit states. And then there are 3 commands that give 24 possible cases. And then you coalesce a bit and figure out what cases are actually the same case, and you figure out there are 10 cases to handle. So those 10 cases can then be done in a stated model. So here's an example. C, K, and T is the concurrency count, which can be 0, 1, the queue size, which can be 0, 1, and the token count, that can be 0, 1. So one of the cases is this. There's a concurrency count we don't care about, and we are trying to queue a new packet, that's the queue here, and there's nothing in the queue and we have no tokens left. In that case, the only thing we can do is to queue the packet. So the transition for the model is, there's one thing in the queue, there's still no tokens left, and we do not do anything with the concurrency count, right? This one is the other typical example. You're done, and there were tokens. In this case, we have one worker that is working. He's saying, I'm done. We have one in the queue that is waiting to do work, and we have a token we can pair him up with. So the result of this is that the guy that were in the queue is now the guy working, so that stays 1, but there's no one in the queue anymore, so that goes down to 0. And we took the token and paired it up with the guy in the queue, so that goes down to 0. So you build these transition diagrams, which defines how the state transitions in the system are. And there are 10 of those. And then you define a model for those 10. And then what you do is you randomly run these state transitions, and whenever you do it, you query the underlying system and ask it, are you in sync with what my model says? And note that we do not care about ordering on the queue. In this case, it doesn't matter, but we do not care about all these things. We only care about the basic things. And that is the count. So now we have a model we can build up. We can check that our system under test actually behaves like this model is saying. And then you generalize. Now we have a simple 0, 1 thing. So we generalize. We say there can be k elements in the queue, and the token count can be t, and c is arbitrary. In that case, the old one, we had this 0, 1 case, but in the general case, it's basically a -1 and a -1, right? We move one of the things from the queue over into the set of concurrent workers. And the more general one is you move more because you have more that can start. Then you add time to the model, so now time becomes, so I have a basic model now, so I can begin augmenting the model with more and more stuff. So you add time, you add arbitrary process crashes, you shoot random processes and check that the system survives, and so on and so forth. So with this simple 0, 1 model, bitwise model, I can start with that, and then I can extend it systematically by doing these things. So what is the outcome of this? Well, it already found 4, 5, 6, 7 bugs in there. And the code is very small. There's less than 400 lines of code in this project. And still it finds 6, 7 bugs. I run in 30,000, 40,000 tests every time I did a change, something like that, just for fun. It takes a lunch, something like that. The CoDel stuff also has an EQC model, but it is simpler because there's not that much I can check inside it. But I can check that it doesn't crash. I can do my simple post-condition check, which is nothing, it's trivial, but nothing must crash in there. And I do check certain simple things that if CoDel is dropping, then actually there's a drop packet along the way and stuff like that. I guess I'll take questions, but I can also show code if needed. How are we for time manage? 5 minutes? And then I'll just take some questions, and then I'll show code later. Yeah?
I use DynamoDB quite a lot.
Right.
And you want to maintain a certain level of write units.
Right.
So it's not that you want to do 5,000 requests, you want to do 5,000 write units in terms of DynamoDB ones.
Right.
So it would be very useful for me to say when the work is done.
Right.
Right.
Would this somehow be possible? Certainly. But you need to come up with a QuickCheck model for it. Yep.
Did you mention the overhead?
There's considerable overhead with the solution. I have a single gen server on which I hinge everything. I thought about trying to avoid that, but I wanted the model first. I thought that getting the model for this was more important than getting the speed. There's ways by which, so there's several ways by which you can speed this up. One is that you can go approximative, but then it's very hard to define a model for it. So you could do it approximately rather than doing it explicitly. I'm trying to make the fast path where you are allowed to run very small. So I'm trying to make that fast path as small as possible inside the system. And there's a reason for that, because this is the common case. If you get queued for some reason, you're probably going to be queued for milliseconds anyhow. So if you get queued, it's not that much of a problem. The problem is if you get allowed, because that is actually the fast path where I'm putting on latency, right? But I haven't really measured up to more than 5,000, 10,000 in the limit, something like that. It works kind of okay up to that level. I do not know if you have 40,000, it depends on your rate into the system. And if your rate is too high, I do not know what will happen. It'll probably be slow. That would be my guess. There's very little tuning in there, so one could tune a lot. And now we have the model, so tuning is simpler, right? You just rerun the check, and if it works, it probably works. Yeah. Tom?
You can shoot me afterwards, because I should probably check your blog.
Uh-huh.
There's manifesto.
Uh-huh.
What's the link to that?
There's no link yet. It's not on my blog.
Okay, good. It's already hashtag.
It's on GitHub in the Safetyvalve repository.
It has to be more public.
jlewis/safetyvalve on GitHub.
It has to be more public.
Yes.
So we can subscribe to it.
Oh. Yep. More questions? Yeah.
For example, I'm doing a REST resolve.
Uh-huh.
I have two types of things to consume.
Right.
Authentication, which can be costly but not much.
Right.
And the real database job, which is costly.
Right.
Does it make sense to put two queues?
In some situations, yes. It depends.
One is more generous and second
Right.
is more
In some situations, it probably does.
will
Yes.
behave nice.
Well, two queues means two gen servers inside the system. Currently, there's no cross-pollination between the two queues, so they act completely independently of each other. But I know jobs can do much more here. It can actually watch over the node and then do stuff when the node as a whole becomes overloaded. But I do not have the model for that yet. So I haven't added it. This is the last one.
Okay, chicken and egg question.
Uh-huh.
How do you get the first millions of the dog food requirements?
The first users of this?
So how do you get the first requirement to start coding?
Oh, well, the point is that you have to have the model first, right? So it has to start with the model.
Yeah, you also have to have features to implement, otherwise you have not.
The dog food thing. But then it isn't that hard, right? I actually wrote this because I'm tracking Quake jewels. And I needed, so then I had the dogfooding principle. I needed some kind of limitation because apparently a Raspberry Pi can kill the Quake live site. And so that was the dogfooding thing. And then I needed the model, right? So you can start, there's an escape hatch that makes it possible to start, I'd say. So I don't think you found a bug yet. Yes, thank you.